My last visit here was in '03 when WINLAB used to be in the trailers. So I hope all of you appreciate this new environment. I certainly do. So, okay. So what I'm going to do is I'm going to skip some of the preliminaries. Oh, where are you? Okay. Oops. That's not a good sign. Okay, so here's the outline. So I'm going to talk about, this is really slow. So let me get back to that show. All right, so I'm going to talk about multi-hop or mesh networks. And now it's fast. Okay. So, and I'm going to skip some of the preliminaries, so that at least I think for this audience you don't need all the detail. But what I wanted to focus on is my interest is really on scalability. And I was telling Professor Ray Chaudhary that unless you're at WINLAB, you cannot do scalability research probably anywhere in the world. So again, you should appreciate that you are here. My scalable platform is OpNet, with all its bugs at the physical and Mac layer that we've been trying to fix. And my hardware testbed has like 2 students and 4 nodes or 6 nodes, 6 client AP pair nodes. Okay, so although we are all very interested in the high density problem, which is the problem both from a business standpoint and from an intellectual research standpoint, I certainly believe the high density mesh, in this case .11 mesh. To solve the high density problem, one of the things is that you want to answer how does this such network scale, right? As you well know, that all of the current, you read the literature and you look at the current .11 networks, they're all designed for coverage. They're essentially meant for the home. They were not meant for density, right? They were meant for low density. And they're all designed for coverage. And this new paradigm, i.e. the next generation of .11 networks, is meant for quality of service, for end user bandwidth, guarantees. So you are basically seeing almost a 90-degree or 180-degree shift in the design philosophy, which is why I said it's both a very interesting business problem and it is a very interesting research problem. Okay, and the tools don't exist really to solve the problem. Which I mean, both the academic tools, at design, analysis, optimization, plus no testbed other than Orbit, in order to get some insight how we are going to handle the problem. So now, when I say key approaches, this is the, so this is a multi-dimension. As anyone will tell you, there are many dimensions to the problem, which makes this both challenging and interesting. And any one professor with a few students, you only attack a small slice. So this is what I have been doing. One is, as you well know from the Orbit nodes, they're all multi-radios. So the fact is that the availability of hardware is cost incremental. You already have default ABG cards, and if you have you'll have 11N, you'll probably see ABG and N, coming out in the near future. So any node default is multi-radio. Okay, so it's either multi-mode of the same version or actually different, physical radios. They will all be integrated, in some platform like a laptops or PDAs or cell phones and so on and so forth. So to focus ahead on multi-radio, I think is a very, very important part of the optimization. Okay, and then the other is protocol stack optimization that everyone knows. But the important feature, and this is why I put the word adaptive on my website, is that the optimization problem offline is usually so hard, and because there are so many parameters that you really cannot, put a mathematical formulation and really get an answer. What you can get is you can maybe get partial answers, and those answers are not going to be robust. So one of the things is you shouldn't spend too much time over designing it or having a huge problem and then finding the right answer for that problem, because the moment you go to implement that on Orbit, you'll find it crashes and burns on your head, right? So the idea is just to use analysis to get a guide. Hopefully your analysis is a starting point for online adaptation, which is where cognitive radio or software-defined radio or intelligent radio or smart radio, whatever your favorite buzzword is, really becomes a driver of the next generation. That you will design something offline will just be a guide. You'll go ahead and implement it, and hopefully what you design, and this is what you should be doing, designing for robustness rather than optimality should be your guiding principle. Get rules which are robust, which you can then tune online as you identify an information gathering mechanism and a control plane, okay, to adapt. All right? So I think, using multiple radios, redefining the protocol stack, and so what are all the versions? Well, what are all the parameters? We want to tune, for me, carrier sense threshold. We want to look at rate setting. We want to look at channel allocation, channel setting. We want to set the transmit power of the nodes. We want to set transmit power of the clients. We want to send receiver sensitivity of the clients. And we want to be able to use the appropriate, link-aware routing metrics. So there are at least like 7 parameters that you would like to jointly optimize. Okay? And I think there is lots of thesis work, in trying to take 2 at a time, 3 at a time, and finding optimality principles, which I think are guides, robust, rather than being right. You'll probably not find things which are optimal in any sense, which will actually work in practice. All right. So as I mentioned already, the old networks, or you can say the legacy networks, are all designed for low density, and those are home networks. And what we are really looking for is this new frontier of HD or high density wireless LANs. And in any typical deployment cycle, whether somebody is doing a business deployment or Ivan is doing the deployment here, what you have to do is you're going to plan for the network, right? You're going to figure out, let's say this is typically a business deployment. You want to figure out what coverage, what capacity, what throughput users want. And clearly for high density, these capacity throughput provisioning, it becomes the driver for the design. But anyway, once you're physically installed, which is you know where to set your APs, configured and calibrated them, i.e., provided channel settings for the APs, figured out calibrations for their transmit power, you need to monitor. So this is the huge amount of database that you get. Based on this monitor, you have to do troubleshooting and management. And then then you're going to need to optimize and redo the planning. So this is a very informative loop. And my point is this, that I think in the planning stage, it's better to be robust than be optimal, and the optimality can come later. Okay, based on. So I already mentioned some of this. You want to select number of APs, place where the APs, do a channel characterization, figure for loss of path losses, small, shadow fading, small scale fading indoors, determine cell size, select channels, so on and so forth. So, okay, so I'll skip all of this because I think this is mostly background stuff. So let's look at .11 operational modes. So everyone knows that in .11 you have this infrastructure mode where the clients, as soon as you open up my laptop, it starts scanning, and you seek to associate with an AP, looks for beacons. Or you can, in principle, the protocol also supports the ad hoc mode or the independent BSS mode. So all my talk pretty much will be in, for the infrastructure mode. This is where you're running most of your experiments here, and I'll skip this. These are client, basic stuff. Okay, and I will move over. So here you have basic service set. And the important thing to realize is that currently, all of these BSSs, these basic service sets, each AP has a wired Ethernet connection, right? So right now, all of them have IP addresses, they're IP addressable. And in the future, here's what we would like: a collection of these BSSs or basic service sets is called an extended service set. And because every AP has a hard Ethernet connection, the backbone, which is this wired Ethernet backbone, becomes a distribution. So, much of this, the legacy .11 network is really meant for, connection, one-hop connection. It's basically a one-hop wireless connection to the internet, much like your cellular system. But what you would really like to do is, look ahead to the next generation, we would like to have wireless interconnectivity. That means change the distribution system from being wired to being wireless. So this is the current wired distribution system. Okay, so you have a basic service set, which is basically like a cell, all the clients which contain, through CSMA, CA for the resources of this AP. Similarly, another cell, Okay, these hopefully to mitigate interference are on different channels, and they are all connected hardwired to the backbone. And now what you would really like is remove the wires from these APs and have a wireless connectivity, wireless interconnectivity. And the idea is this, that these only a fraction of these APs will have a hard connection to the internet. So maybe X% will be what you would call gateway APs. So the data from any client, either to or from any client, will multi-hop through APs till it gets to one of these gateway APs. So in such an architectural vision, the mesh or multi-hopping becomes inevitable on the infrastructure side. So the APs will support multi-hopping, and pretty much the scalability. So the way I think about it is that you have two tiers. You have a client tier, and then you have a tier 2 which has multi-hop. Okay. All right? And so what we are looking here is the scalability of this second tier, which is a tier of access points. So, all right. So so today, this is just basics about dot 11. If you have a single cell, as you know, the throughput will decrease as a function of the number of stations which is contending. This is simply due to the overhead of CSM-SCA, the loss that you have in contention. So this is just to tell you what are all the ways today that you can do network optimization. You can do load balancing. If you have too many stations clustered around one AP, but other APs have fewer stations, you should, in principle, think about reassociating some of the users from the more loaded AP to a less loaded AP. Now, you got to be careful. This is not always. It does not guarantee that you're going to increase the aggregate throughput. You have to do this carefully because you need to consider a trade-off. Because if I transfer a user, let's say with rate 1 megabit per second, which is sort of a user at the boundary of one AP, onto a second AP which only has like 11 megabits user, what you will do is you will lose more than you gain. So there's always a trade-off in transferring users. So for example, let me give you this picture. So if you have, say, two APs, and both of them are 11 megabits AP, so these are two APs, let's say just to make this simple, it has two rates, 11 megs and 5.5. This is the internal 11 megabit rate. The outer circle supports 5.5 megabit rate. So what you might want to think about is that the users at the edge here, and if you look at this, there's an asymmetry in the loading. So this AP1 has many more users associated than AP2. So for example, these purple users are all associated with AP1, and what you may consider is moving some of these users. Like, so for example, this user gets 11 megabits from AP2. Clearly, it would only get 5.5 megabits from AP1. So logically, this user should associate with AP2. But if you look at these purple users, they are getting 5.5 megabits either from AP1 or AP2. And in this case, you would expect that if I reassociate some of these purple users, which are in the 5.5 megabits belt in AP1 to AP2, you might likely to see an aggregate increase, right? But not always, not all the time. If, for example, you have a user here which was associated on getting 1 megabit per second, and you reassociate with AP2, it might bring down the aggregate throughput of AP2 more. So basically, what you're saying is, as I'm using reassociating some users from AP1 to AP2, the contention here is reduced, so the aggregate throughput of this cell increases, and here it will decrease somewhat, but the increase from AP1 is more than the decrease from AP2, so overall it should increase. But you got to be careful, right? So it may happen in some cases that when you reassociate, you might actually not see any improvement or actually bring it down. So, but in general, you can do these sort of load balancing optimizations. Certainly, setting the transmit power of the APs is important. And this points to the basic fact that in high density wireless LANs, the key thing is managing interference, right? And managing interference, in the current protocol stack, we manage interference all over the place. We do it at the physical layer through coding by making the link more reliable. We manage it at the MAC through the back-off mechanism in CSM-SCA, right? We manage it in layer 3 in the routing by putting what we call link-aware metrics in the routing algorithm, in the routing metric. Okay? The algorithm is different to find the route, right? So the point is that in high density, the name of the game is to manage interference wherever you do it. And the point, and the simple answer is you have a set of paradigms or a set of parameters where you manage interference across all layers of the stack. And there is increasingly compelling case that you need to do all this jointly. Okay? So what are the parameters? Certainly transmit power is a parameter, right? Okay. In the MAC, in the CSMA CA MAC, setting the CW min, the CW max, and the back off, that's a parameter. Receiver sensitivity and carrier sensing threshold, these are again interference parameters, although CW min manages collision and PCS threshold and receiver sensitivity, manages broadly what's called interference. So here's an interesting definition that I like to ask people. What is the difference between collision and sort of physical layer interference? You have to ask the MAC guys. So for the MAC guys, the definition of collision is in CSMA is that two stations initiate transmission at exactly the same slot. Okay, so it's basically synchronous interference is equal to collision for a MAC, right? But for the phi people, if I have two packets and they overlap, one transmission starts before and one starts after, that's interference, whichever way this is. So again, these are sort of fictitious, partitioning of interference, So I think what we have to learn is that from our experiments, both in OpNet or particularly from test beds, managing interference is a cross layer, this thing. And how you manage using all of these different attributes, okay, I think is probably the most important, advances that you're going to make. Okay. So here's the question. If you read the literature, how do you set the transmit power of APs? So if you look at ad hoc networks and you look at the Gupta-Kumar type work with the assumption, you would get from that paper that you should set the transmit power to as low as possible, subject to the condition that you maintain one-hop connectivity. Okay, to optimize the aggregate throughput like Gupta-Kumar, if you read those sort of work, assuming their traffic model, you reduce the transmit power subject to maintaining one-hop connectivity. However, I think if you do simulations and you assume that all the APs have the same, have same transmit power, you can actually increase the transmit power from a minimum and actually get increased throughput. Okay. So it's not very clear. Okay. So what is the rule for setting transmit power, right? Is it so there's all kinds of sort of, depending on what your assumptions are, all kinds of sort of different quote unquote optimal settings for what the transmit power should be. Okay. All right. So in summary, we all want to get increased capacity to the user. Well, what do? Well, you can always beg for more spectrum, and the assumption is that you are not going to get more spectrum. So given that you're not going to get more spectrum, you have to shoot for one of these. You've got to go shoot for better spectrum usage. And what does better spectrum usage mean? It's not just fixed point optimization, get a better phi, right? Better spectrum usage really means, so this is, sort of the fixed thing, get a high level modulation, all the things that the phi layers people do. Get a more efficient MAC, strip the MAC. That means the MAC overhead, So this is one of the things, I don't know if you know that from a modem designer, there's this obvious paradox, right? The modem designer gives you 54 megabits, 108 megabits, sort of megabits, and the MAC efficiency goes the other way. Sort of 54 megabits link, the MAC efficiency may be 65, 70%, and for a 108 megabits link, the MAC efficiency goes to 50%, right? So here's, like for example, MIMO, if you look at, having a MIMO MAC which is backward compatible with a non-MIMO MAC, the overhead is going to kill you. Because you're going to be transmit preambles for the non-MIMO and the MIMO, so the MAC efficiency is going to go down. So you have to solve, these very sort of engineering things like getting a MAC which is, at least as efficient you can. Then you need the protocol. So for example, CSMA CA, the efficiencies for contention due to the protocol, you need to be able to manage that. Okay, so this is what I call, interference management. So having, of course, for the given spectrum that you have, enhancing frequency reuse, or in this case spatial reuse, is very important. As I said, of course you're going to use MIMO to improve the raw channel rate, but controlling topology through transmit power, through carrier sense threshold, through receiver sensitivity is going to be pretty critical. And I'm going to talk a little bit about our results. And this is something increasingly that's important. Now when you have a bunch of nodes, right, and you have a multicast or a broadcast environment, the same data from one node is going to be residing in the network at multiple places. And so newer network architectures which are based on relaying or collaboration between these intermediate routers becomes in principle possible if you provide the abstraction for them to exchange information. So for example, intermediate nodes that can collaborate or relays which can collaborate becomes a possibility. So newer architectural principles which help in the routing. Okay. So all of these are now open for as design considerations. And so I just wanted to sort of lay it out that there are all of these dimensions to this problem. So anyway, so this is the current wireless mesh network. We begin with coverage, and you now want to add designing for capacity. All right. So let's see how we want to do this. So the idea is this: a solution, if it's to be sort of practical in the business sense, has to be cost effective, right? If you want to have a dense deployment of mesh nodes, each node has to be cheap, all right? Cheaper than a few $1,000s. It has to be maybe $100 AP that you can put all over the place. Currently, as you know, APs for the enterprise environment aren't that cheap. They're not in the $100 range. For the home it is, but not for for the enterprise deployment. Why? Because there are these fat APs which have the entire Phi and Mac stack plus the cost of the hardware connectivity. You have a complete Ethernet backhaul. So a multi-hop network, you must have cheap intermediate nodes or routers which act as relays. So you really need soft nodes, right? And the idea of multi-hop, this is the classical idea. You need to preserve power by having smaller hops. And having smaller hops allows you higher link rates, gives you, of course, power efficiency. And hopefully, by doing all of those import and interference management, you can get better spatial reuse. That means you can allow multiple co-channel transmissions to go on at the same time, right? So all this is the good news. But what's the bad news? If I'm now looking to go end to end, so now I have source wants to sense to destination, right? Okay. Previously, if you had a high power transmitter and you send it in one hop, now you have a low power transceiver and you're sending it in multiple hops. The end-to-end throughput is going to degrade because of these multiple hops. All right. So now you have to balance the positives of a mesh with the potential negative. Okay, and you have to figure out how you can have a mesh architecture in which your throughput really doesn't degrade as you increase the network size. So you want to provide, there are many ways you can think of this. You have a given area, right? In that given area, I'm increasing the density of nodes. So that's typical one way we study scaling. For a given area, I increase the node density. As the node density increases, the average number of hops for a route increases. There you have you will see the degradation in throughput unless you actually do all the things that I mentioned. Okay. The other way you can think about scaling is you take a link, you fix a link distance, right, and then you scale the area. Right. We typically prefer to fix the diameter of the network, and you want to scale in terms of number of hops. You want to scale the number of nodes. That means the density. Okay. So there are two different ways that you can study scaling. All right. Okay. So I mentioned several of this already, so I want to move over to as soon as this responds. So what I was going to show on this slide is that based on so I'm going to talk essentially about .11 meshes. So this is a peer-to-peer mesh, okay, based on the ad hoc, the independent BSS mode, which we won't talk about. So I think I can skip one more. So the mesh that we talk about is really this sort of a hybrid mesh in which you have clients all clients associate, they all form cells, and the mesh, the multi-hop is between access points. So, okay. So having said that, okay, I already mentioned much of this. So let me go back to mesh scaling basics. So as I said, my interest is to look at capacity throughput scaling. So if I look at the aggregate network throughput, right, and in the beginning, let me make this simple. Let me just have a lot of one-hop connections, right? The idea is, end-to-end connections is sort of monotonically related to improving one-hop lengths. If I improve the one-hop throughput, you could expect on the average that the end-to-end throughput is also going to scale similarly. So let me just say that if when you read network throughput, there's a lot of multiple one-hop connections are going on, and I'm measuring the sum of all the aggregate one-hop throughputs, right? Okay. Now, so the important thing is there's spatial reuse. There are a lot of multiple co-channel one-hop connections which are proceeding. Okay. So the aggregate network throughput is some function f, some complicated function which we don't know what we are trying to either estimate or through simulations or observe on the test bed. We know it's a function of monotonically a function of link capacity. If we increase the link capacity, the throughput is going to improve, right? So the link capacity is related to the throughput by minus the packet error rate that you see on a link, and then if you subtract out any MAC overhead, that's roughly the notion of capacity that you're going to see based on any link. So how do you increase the link capacity? Well, which already it's implemented. Any link layer is adaptive, all right? You do have adaptive rate, modulation, adaptive rate coding. And with 11n, you're going to use MIMO. So you can increase the link layer capacity by any of these techniques. Pretty much of my work, and I think this is much of the interest here in WINLAB, is that you can improve the link capacity, you can improve reuse of your given spectrum, and you can improve the allocation of those resources. So I just break this out just for sort of clarity. Under spatial reuse, I put tuning of all the parameters of sort of the topology control parameters, transmit power, carrier sense. Okay. I also put channel allocation, right? And actually, I should have put link-aware routing metric, here. This is sort of an artificial separation. Here's what I call sort of low-level MAC, lower MAC type parameters, and link-aware routing and multi-radio utilization, which is binding channels to interfaces. I call sort of the scheduler or the upper MAC, if you want to think about it, right? So a lot of the things that I'm interested in, and possibly a lot of you are interested in, lie in this box. Okay, and I'm going to talk about our work on improving spatial reuse, and to do that, I want to give you a little bit of background. This is sort of summarizing intuitively results for meshes with a single radio. Why meshes with a single radio? Because in orbit you have multi-radios, okay, and much of my focus is to try to understand what is the gains that you get with multiple radios per nodes. When I say multiple, think two, okay? Think two radios. Why two radios? Because if you look at the tier 2 mesh, if I have two radios, let's say I have a BG and an A radio, I can use the BG radios to aggregate traffic from the clients, and I will use the A radio for multi-hopping. And since BG and A are in orthogonal channels, this is a good, all right? So, and you will see, I don't know if you've seen if you look at the literature, there are several companies which have implemented a 3 radio, okay? So several people make a claim that actually 3 radios is quote unquote optimal, all right? And you can see this. So let's start with 2, and you can, so the idea is going to be this. Number of radios per node, it's not going to exceed 3 or 4 at most, right? Okay, even though the cost is incremental, there's a cost, and you're going to have, you can't have 10 radios per, 10 A radios per node. So it's going to be 2 or 3. The number of channels, hopefully, already with 11, you have, many more channels, 11 orthogonal channels. With A, you have, 11 or 12 orthogonal channels. So the number of radios is going to be still a fraction of C, the number of orthogonal channels available. And that's the regime in which you want to see what is the impact of the number of radios, right? To understand that, we want to look at a single radio, single channel baseline, okay? So this, again, much of this work is all simulation. So this goes back to a Mobicom paper by Robert Morris, etc. in 2002, which says, okay, if I looked at a very simple, again, by the way, the other thing is that if you look at the simulations, particularly in the computer science community, very limited topologies are simulated. There's certainly, other than an analytical work of the sort of Gupta Kumar and all of this work, if you look at hardcore simulations, it's all either line networks or grids, and far fewer on really random ad hoc topologies, because simply it's hard to make sense as to what design parameters contribute to what impact on the aggregate throughput. But for line topologies and 2D grids, lattice grids, you will find more conclusive simulation evidence. So let me quote the most conclusive simulation evidence from a O2 Mobicom paper by Morris, which says that if you have a line topology, right, and each node has only one radio, and they all operate on one channel, in general, of course, as I said, the throughput, where n is the number of nodes, goes as 1 upon n to the a. Okay, this is the aggregate 1-hop throughput, and if you assume everybody is only transmitting to the nearest neighbor, goes as 1. What does a depend on? A depends on topology, and so can try. For the line network, a is roughly equal to 1. Okay. Okay, why roughly equal to 1? So I said for a linear chain throughput, why this is roughly equal to 1 is very simple. Now this depends on, this is where it gets interesting. If you look at the settings that they have used in their simulation for things like carrier sensing, the transmission range and the interference range, what this means is this. I have a bunch of nodes, right? I have a bunch of nodes. Effectively, there's only one transmission going on in that node at any one time. There's no spatial reuse, okay? So if I increase the number of nodes, right, I'm not increasing, unless I tune the phi and mag to actually improve spatial reuse, I'm going to get 1 by n. If I have C orthogonal channels, well, I can, use the degrees of freedom of those orthogonality. I'm going to get C by n, but it's still big O of 1 by n. If you want to improve things from 1 by n to something which is slower than 1 by n, you got to improve spatial reuse. Okay, so for example, the Gupta Kumar ad hoc work in this sense, so you start reading these papers, and this obligatory sentence which I never understood: the pessimistic result of Gupta Kumar. So I ask yourself, why is it pessimistic compared to what? As a matter of fact, if you do simulations, and Gupta Kumar's result is 1 upon root n or root n log n, right? Well, root n log n is better than 1 by n. So as a matter of fact, in simulations, you can get any number of results which are more pessimistic than Gupta Kumar's, which makes Gupta Kumar look optimistic on the average. All right. There are lots of examples where you can get worse than 1 by root n or 1 by root n log n. Okay. And so be careful of what you read in some. So the point of this is, with a single radio, single channel mesh, there's not much hope unless you put in spatial reuse. So how do you get spatial reuse? Of course, I can use orthogonal channel, but the main point is I can tune transmit power, carrier sense threshold, right, to actually improve the number of simultaneous transmissions. The number of simultaneous transmissions that you can go on, which will become a multiplicative factor on 1 by n, is of course some function of n. Okay, maybe log n, something, or some n to the power 1, gamma, where gamma is something less than 1. But that's what you're trying to optimize, or that's what you're trying to make enable using tweaking transmit power, carrier sense threshold, receiver sensitivity, all of these 5 MAC parameters, as well as collision window, all of the things for interference management. So here's the other thing. So this is something Suppose even if I give you single radio, I give you multiple channels. So let's say I use a 1B radio and I have 3 orthogonal channels, right? You can improve throughput. I can improve throughput, but what does it do to the delay? Well, as you know, the switching delay in .11 actually today kills you. All right. So the end-to-end delay is actually today lower bounded not by packet transmission time or the transmission time it accesses the channel. It's actually lower bounded by this fixed number, which is this large switching delay. Unless technology improves, you're not going to get, that number, the lower bound is not improving. And so the fundamental problem with end-to-end delay is the fact that because of this switching and because of the fact that these nodes are essentially half duplex, right? So we know that one of the main drivers why you want to have multi-radio nodes in principle is that if I have 2 radios and I have multiple orthogonal channels, okay, I want to be able to receive on radio 1 on channel C1 and transmit on radio 2 on channel C2 simultaneously, where C1 and C2 are distinct. right? Currently, I can't do that anyway with a single radio, right? I have to receive, and then I have to turn around from receive to transmit, and so it's a half duplex. So being able to use nodes in full duplex mode actually is pretty fundamental to increasing capacity. It's a very, very simple idea. Now, unfortunately, the hardware today, that if you put two sort of daughter boards, stack them together, and you have one guy on channel 3, another guy on channel 11, unfortunately, depending on how close they are, there is so much of crosstalk on so-called orthogonal channels that it doesn't seem possible with today's hardware that you get the benefit of orthogonality. Okay? But certainly, at least, this is the direction that we should be looking at, right? Particularly to solve the delay problem, all right? Okay, so even with having multiple channels, maybe you can scale throughput, but you're not going to solve the delay, the end-to-end delay. So,
I have a. If you move the antennas apart, solve that problem.
I mean, you can mitigate the problem. So people have said this, that instead of stacking the board, if I move the boards, if I have the antennas separately, it mitigates it. But I think the experience is there's still a lot of work to be done in shielding and so on, so forth we don't understand. So
the problem is if you have 8
yes.
crosstalk.
You can give crosstalk even with two antennas, say the way they are separated 1
So
meter apart.
there is a power amplifier
Yes.
sending signal at 20 dB. So if you have a leakage of say 60 dB below,
Right.
which is huge.
Huge, yes.
60 dB below, that's still way above sensitivity
Of the receiver, yes.
right? So in theory, if you
Yeah.
have just a little bit leakage on any of the connectors or PCB or anywhere,
Right.
you could actually get the other card to start receiving that, even if you are 3 channels.
3 channels, yeah. So, but but in terms of this, these are the right things to look at. And today we have to find fixes and to work around the problem. But hopefully in the future, this is really how you are going to scale. Find workable solutions for scaling. So what we did is, so this is all OpNet. This is my test bed. This is all OpNet simulations. Okay, and so if you look at, I have this nice 2D grid. And I have these nodes. These are both transceivers, and here's what we did. We did use these 4 channels, 1, 2, 3, 4, and you can see that I connected. So you can randomly assign these channels. Well, it's not random, and you can see that if I look at so these are all single radio. Okay, so if this guy wants to transmit a packet to R2, it sends it on channel 3. And then if R2 is to forward that packet, after it receives this on channel 3, I have to switch that radio to transmit mode to channel 4 and then send it to R6 and so on and so forth. And what I wanted to show you was, okay, that, I skipped the result, which is the end-to-end throughput. Let's say if I set up flows from, say, R1 to R16, actually numbers are very significant. Okay? So anyway, so I'm going to skip this. So the first key result which I wanted to talk about based on our work is about throughput optimization using adapting the carrier sense threshold. So I was mentioning, so I'm going to make this quite simple. There's some analysis in this paper that I'm happy to show you. Is that this physical carrier sensing is a mechanism in which all of you know about the hidden node and the exposed node problem. So this is the classical discussion about how CS in a multi-hop environment, CSMA CA does poorly because it doesn't account for the hidden node. So what is a hidden node? Hidden node is this term I don't like. Hidden node. This is sort of typical MAC layer term. But basically, what you have is this: you have a receiver, and the receiver, which is receiving from a desired. So they have what I call a reference transmission. Okay, nearly there. Yeah, so if you actually have 2 flows here, then you can see that because it's half duplex and it shares this between two flows, the end-to-end throughput falls further to R by 4. But then if this is with one radio, but if I get two radios, I can bring this up to R by 2. So this is simply by showing, the point is that if you have multiple interfaces here, and if I discard, any queuing at these nodes, I can actually, with multiple radios, if I assume everything ideal, I can actually increase the end-to-end throughput in a very simple-minded case. All right. So let me describe a little bit about some graph theoretic based formulations for formalizing these approaches in terms of interference avoidance for a multi-radio. So SRSC is a single radio, single channel, and how we can apply these ideas to a multi-radio, multi-channel case. So what we're going to do is this. We're going to define some concepts. So what we're going to assume is this, that in graph theoretic formulation, we have to abstract away the notion of, let's say, signal to noise ratio, and where we say, okay, there's an interference range, and this leads, there's a transmission range, and there's an interference range, and they typically leads to a collision domain, a carrier sense range which leads to a collision domain, and an interference range which leads to an interference domain, which really means the following. Let's assume that for any simple topology like the grid, that if nodes which are simultaneously transmitting, if they're one hop away from each other, they will collide. But if they're two hops away from each other, they will not collide. Okay? So this is a very simple abstraction. So that therefore the set of nodes which are two hops away from either any transceiver, they will not collide, but one hops will. And similarly, there's an interference domain, which is if you have two simultaneous transmitters which are x hops away, which is typically x is greater than 2, then they will interfere, they will collide. And we typically say the collision domain is smaller than the interference domain. And the idea is this: if I look at a single radio, single channel mesh, and I can characterize the collision domain and the interference domain with this definition for a single radio, single channel mesh, and I redo this for a multi-radio, multi-channel mesh, and I can show you that there is some monotonicity property of these domains, i.e. say the number of nodes which are in the collision domain here is actually larger than the number of nodes in the collision domain there, and the number of nodes in the interference domain here is larger than the similar set there, or maybe the sum of the two nodes, because both of these are undesirable, here is larger than the sum of the two nodes there. You start proving some analytical results about
How different are the consequences of the collision and the interference? The collision, you lose the packet at the top.
Same thing. So what we assume is that both of these lead to packet losses. Okay, and you're right that for example, things like capture and so on and so forth are not accounted for. But if you're doing simple graph theoretic models, you don't have that ability to. So in principle, what you would like is you won't like to have these definitions in terms of signal to noise ratios, signal to interference ratios. But this is basically very simple graph theoretic models, which can't make this.
I feel like if you make the same results of packet loss, then they are not different.
Well, so the point is this. Okay, so if you have a collision domain, the collision domain is between two concurrent transmitters, right? So you lose the reference packet from say the transmitter to the receiver. The interference is this, that the packet loss is happening at a receiver due to. So the collision is two concurrent transmitters, right? They collide because they transmit simultaneously as per .11 in the same slot. Here, in the interference domain is at the receive node in a transceiver, due to a secondary transmitter, you get packet loss. So it's a packet, both are packet losses, but the causes are different. So that's why we distinguish this. Okay. So the idea in this sort of formulation is that you can have a graph theoretic formulation. You can say the number of nodes in these two domains is some of them. If these are larger than this, then having multiple radios has a benefit. Okay. So that's the purpose of this. So what we did was in some papers we said, okay, let's assume each node has R radios and a total of C orthogonal channels, and a channel assignment formulation is we want to minimize the number of links which can be active simultaneously. This is to minimize the number of collision, people in this number of nodes in the collision domain, right? This maxima improves instantaneous, we want to maximize the number of links when we access simultaneously, but at the same time we want to minimize the size of any collision domain. Okay, so we want to do a min-max or max-min type of formulation, based on a graph. So here's an example. So I won't give you the formulation, but I just give you some examples to give you some insight, right? So this is what it'll be. So let's say I have, again, as always, my favorite 2D topologies, right? So if this is the reference link, this is a transmitter. So this each are transceivers. So this guy is transmitting to this guy, right? If I use my definition of 2-hop neighborhood, that means when this is transmitting, right? Okay, and this is receiving, all 1-hop neighbors of either the transmitter or receivers cannot be simultaneously transmitting, right? Okay. Why? Because of carrier sensing, this would prevent this from transmitting, and this for 1-hop definition, so the packet that's sent, it is lost. This can't transmit, that can't transmit, that can't transmit. Okay. And similarly, as I said, now by this 2-hop definition, you are going to include these 4 nodes as well. All right. So if this link is on, it pretty much prevents all of the other dash links. So actually, this can't. So all of these dash links, you can count the number of links. These are all off. So if this link is on, okay, all of the dash links are off by this simple definition. So the size of the collision domain of this link is actually 22. All right. Okay. So as a matter of fact, so now you can ask yourself, if I now have multiple radios, is there a channel assignment which can reduce this collision domain, right, from the size 22, as sort of a way to prove that there's some merit in using multiple radios to improve the aggregate throughput. Okay. So let's talk about a partial channel assignment. So so this was done. So let me ask you this. So what we want to do, this is one radio, one channel. We want to go to multi-radio, multi-channel. But let me ask you as a sort of a midway. Suppose I give you 2 channels, but still with 1 radio. Okay, what happens to the collision domain? All right. So actually, with multiple channels, because of channel orthogonality, you can reduce this collision set from 22 to 16. Okay. So as you can see intuitively, if you give me more orthogonal channels, obviously I should be able to reduce the collision set. What happens if I now have multi-radios and multi-channels? Okay. So this is the size of the collision domain for this edge, which is 16, right? If I have 2 radios, I can go from 16 to 14. And so in this simple example, you may think that's not a big deal, right? From going from 16 to 14 in this is not a significant. But this is just a simple example. Let's say if I go from 2 radios to 3 radios, but I keep 2 channels, the size of the collision domain now reduces to 12. Okay, so I'll send you the paper for those of you can go back and look at the details of understanding all of this. So here's one final simulation that we did. Is there some principles of channel assignment based on this formulation in an actual OpNet simulation with say 2 radios and 4 channels that actually improves the throughput? Okay, subject to assigning these channels. So okay, here's a simulation. We did a grid separation of 100 meters. We kept the transmission range R to be 150. So basically, you can only transmit to 1 hop. Okay, so you're not interfering 2 hop away. The carrier sense range, however, is 2 hops away, which is what I said. Is there's a 2 hop a 2 hop silence zone if any node is transmitting. Okay, and what we did is we set up a flow, just one flow in this network, static routing. All right, and we average it over 10 iterations of this, randomly chosen flow. So anytime we set up one flow, and we did this 10 times with 10 different flows, with the link rates are all common. It's about 12 megabits per second, which is about 1,000 packets per second. And depending on, so the way we did these flows was we changed the number of hops. Okay, so when we did this 10 flows, all 10 flows have 4 hops, or 5 hops, or 6 hops. And you look at the throughput for 1 radio, 1 channel. And so there's no channels, but with 2 radios, 4 channels, with the sort of channel assignment we talked about, you can see what is the improvement that you get in terms of throughput. So you get about depending on, you can see the greater the number of hops, the more the significant the improvement in end-to-end throughput. These are all packets per second. Right? So this is just to give you an insight that you can have some rough formulations for even simple formulations based on these collision domain graph theoretic ideas, and you can use the insight from them to actually run some simulations or do some test bit. So sort of heuristics again. This is pretty much in the level of heuristics, and you can actually start seeing real improvements in throughput. And the sort of improvements we throughput, all we're talking about is of the order of maybe 2x. Okay, so there is a lot of work beyond maybe 1.7x or 2x that can be done if we start addressing all the other parameters which I haven't looked at, like I haven't looked at transmit power, I haven't looked at receive sensitivity, all of the other things that you can play around. Certainly by noise injection, you're changing the receive sensitivity of the transceivers. And these all will, depending on how they interact, these all have benefits for interference management. So, this is just sort of a part of the story. Phi layer parameters, carrier sense, we have looked at. I haven't looked at transmit power, receive sensitivity. Here's a channel assignment, sort of classical MAC parameter, right? I have not looked at, we're struggling with trying to implement a link-aware metric in OpNet. We know that will have some, significant impact. And then, putting it all together is, okay. So I wanted to end with this. Oh, by the way, this is okay, if I take a minute, this is a test bed that we have. So we have about 20 Intel IXP-based Star East platforms. And each of them it's basically 2 radio per node. They have 2 daughter cards that are stacked together. And each node you can configure as an APO client, and we fortunately have support for their 2200 driver, okay, which from Intel. And we put it into a simple mesh. So this is what the boards look like. They have these 2 daughter boards which you can stack. Okay, and so right now what we are trying to do is this, since I don't have WINLAB backing me, I can do 4 nodes, or in this case 8 nodes, okay, which is what all my students can do. And right now what we are trying to do is this, we are trying to exactly run, get estimates. Firstly, we are trying to do channel characterization, and then based on the channel characterization, figure out what our carrier sensing, whether I can do, what should be the right settings of the carrier sensing threshold, the transmit power, to measure aggregate throughput if I have, so these are client pairs. So if you imagine this is one cell. In one cell, all I have is one client talking to one AP, all right? Okay, and I have several of these cells, okay? And what I would like to do is I would like to do an experiment where you have one cell and 20, 15, 20 clients all talking to one AP. So we're trying to see what results we get with this. Okay, so we have, we set up IPerf to get link statistics and so on and so forth. I'm already 10 minutes over time, right? Thank you. Questions?